Hey, welcome back.
Hi, Blitz. Yeah, sorry about that, Blitz. Yeah, I've just put it in that trig calculator that I used last time on my phone.
Sure.
And it's come up with the same number, 7,300, I think it is, that you're saying for...
Yeah, so I'm getting 7,389 or
Yeah,
7,390 or so.
Yeah, I simply might have just taken the wrong information from the calculator for the distance to the sun. Or I might have been looking at some of the kind of measurement at the time, but I agree with the number that you've got. It shouldn't really affect what we're trying to find out here anyway from my... Yeah.
Right. So, okay, so that number we can use to figure out how high the sun is above the subsolar point just by, solving for the other side of the triangle, right?
Yeah.
And so that should give us a height of just under 4,600 kilometers. Does that
How much?
match up with just under 4,600 kilometers?
Okay, yeah, I agree with that, yeah.
So then we can do the same calculation for Clint.
Yeah.
And so the same calculation for Clint, we would just plug in all of the same variables, but just change the numbers. And the distance that I would get.
Just one second, Blitz.
Sure.
You've just said 4,600 kilometers, yeah?
4,600 kilometers above the surface of the Earth, yeah.
But that was the number I was giving you at the start. Why were you saying to me it was 730 kilometers? Look, just to show you, because I was getting confused.
I could have said it wrong, or I could have read off the wrong number. I just reran the calculation.
So just to show you, because that's the number I've got already. So
okay, so you have 4,600 or so.
Yeah, here, look.
Okay, excellent.
The sun. Yeah, so I've got the right numbers. Blitz, you're confusing me a bit.
Wait a minute, is that distance to the sun, or is that the distance above the subsolar point?
So it's the distance above subsolar point. Subsolar point, I think.
Okay. So then I do the same calculation for Clint's data, and I get a distance above the subsolar point of just under 5,500 kilometers.
And look here. That's why I've got 55,377.
Okay, so, but I mean, those numbers are different by a factor of 11% or so. So so according to you, so I mean, like, and if my model's off by more than that, right, then your model would be a better fit for the data, right? So that's about an 11% error. So then we reproduce the same calculations and we compare and we check what the globe Earth predicts.
Yeah.
So the globe Earth prediction isn't a prediction about the height of the sun above the Earth. It's a prediction about the radius of the Earth, right? Because we assume the sun is very far away, and we then calculate how big is the Earth in order to produce those shadow lengths. And so the algebra's here. It's not that involved, but the formula at the end of the day is this guy. You take the radius that you get is the distance between the subsolar point and the point that we're measuring at, divided by the arctangent of the length of the shadow divided by the height of the stick. So we can plug this in for your data points and for Clint's data points. And so for your data point, so I'll call this our Riz, what we find is, and I'm just, like I have the calculator, I don't know if you can, hold on, let me unplug my phone. So I just ran that calculation here, S Clint, or there's S Riz, arctangent 1.27, that's your height, or that's the distance of your shadow. And the length of the stick is 1 meter. And the number that we get out is 6,451 kilometers. So let me write that down here. 451 kilometers. And then I do the same thing for Clint's data, which is 70.5 centimeters. S Clint is, just so you can check, S Clint is 3,864. And so we can read that off and we get, where to go? Sorry, I just need to zoom out so I can see. It's this one, 6,292. So this says our Clint should be 6,292 kilometers, which is significantly less error than your model.
Okay, so what I'm trying to clarify first of all is we've only got a difference of, for my model, of 1,000 kilometers, yeah?
Yeah, but
now,
it's like 10%.
we do not know what... Yeah, 10%, but we don't know what the size of the sun is. Can you calculate what the size of the sun is based on the information I've given you for my model,
Yeah,
not for a globe model?
so that is a fair point. We would have to assume, so in order for the sun to have in order for the size of the sun to play have a significant effect on this model, it would have to be large, or it'd have to be not small in comparison to the distances present. So we have these distances of a few thousand kilometers. If the sun was like 1,000 kilometers across, then yes, that would come into play. But because I think we have to assume that because if the sun is only a few thousand kilometers up and it appears small in the sky, I don't think that we can assume that it's a few thousand kilometers across, right? So we would have to, we, in principle, I suppose we could introduce that as another independent variable, but then we would need a third data point.
Okay. Well, I've got that on the other experiments, yeah.
Yeah, so we could do that. That would make the math a little bit, well, okay, but then we have to ask.
We don't need to do that today. We'll carry on with what you're saying, because I want to make sure the globies get there. And I'm not being derogatory to you, Blitz. I mean, just so that we can, so we can be on. So. Yeah. No, but I'm not directing that to you. I'm directing it to the people in the comments and the people who say, I haven't provided data, this, that, the other. They don't realize that I have provided data.
Yeah.
You've been busy.
For everybody in the chat, he provided me like detailed experimental data. Like the experiment was repeated like 5 times in 2 locations. It was like the data. It seems like the data is actually like quite good. So no complaints there. The only the comparison between so if we then look at my data suggests that the Earth has a radius of somewhere between 63 and 6,500 kilometers, and with an error of about 2% or so. Actually, I could work out the explicit error if you care, but it is a smaller error. I mean, like that should be clear. Also, and like you can look at my algebra. I didn't put in the radius of the I didn't put in the actual radius of the Earth anywhere. But this does agree with the radius of the Earth if you Google it. The radius of the Earth if you Google it is 6,371 kilometers, which is just about in between these two. It's actually almost exactly between these two.
Okay.
So I mean, like the evidence isn't looking great. I hope you can see that like this is definitely more closely matches the experiment than the results that you have in the flat Earth model. There's a little bit of leeway perhaps for the solar size, but I don't think that'll help you much.
No, Blitz, there's a few things you're missing out here, unfortunately, because you one of the things that we talked about here was trying to work out whether the sun was local or far away. Is the sun from this calculation showing you it's 93 million miles away, or is it showing you it's local by using 2 triangles? What does it show you?
The calculation I'm showing you right now?
No. So, if you take the triangle that is drawn by me to the subsoiler point, and then the triangle that's Clint's done from the subsoiler point, and you use both of them, you should be able to work out that the sun is not 93 million miles away, but it's local. Would you agree on that, or would you disagree?
The way that you use that the way that you can use those 2 data points to determine that is if it's truly local, the heights that you observe the sun at should agree with each other. Like the H values that you get in both cases should match. That's the check there. Because basically the only free variable in that calculation is the height of the sun. And so when you take that data point tells you if the sun is local, it is at this height. And so the fact that that the calculation says for 2 different locations, it says if the sun is local, it's at 2 different places, says that our initial assumption couldn't have been correct.
Okay. So there's 2 different variables that we've got to take into consideration here, yeah? So on this day, I worked out the sun moves at 250 miles an hour, yeah? That's how fast it was traveling, because I worked out from the different distances it was covering from both locations.
Well, so that only... Oh, yeah, okay. So you mean like the subsolar point is that far, is moving that quickly?
Oh, yeah. So if you look here, these figures here are for Nottingham. The sun travelled 81 kilometres, 133 kilometres and 67 kilometres. And that's between the times I took the points. Now for Clint, it's double. So you've got 276 kilometers, 82 kilometers, and 206 kilometers, which shows the ratio for the smaller circle for the sun for the northern hemisphere and the
I don't
larger
follow.
circle for these. Okay.
But shouldn't, I mean, the sun is moving over a subsolar point, right? So one would
Correct.
think that there would just be one value in both our models, right?
Yes, I agree. The sun over the subsolar point. I agree that the sun will be directly above there. What I'm trying to say to you is one of the areas that I came on a common agreement, which was Google Earth. I said to you that I'll use Google Earth for distances just so that we can get on with this kind of experiment and make sure we can try to come up to some location together. But based on the distances the sun is traveling, it's showing me that in the northern hemisphere where I am, the sun is traveling a smaller distance, which is observed by the sun elevation or angle not changing very much over a period of time. Compared with Clint, it changes a lot more.
How did you calculate those
over
speeds?
the same those speeds.
Or the
basically,
distances, rather. How did you calculate the distances?
Yeah. Okay, so I took the 4 subsolar points. So here we go. You've got the times that I took every result for both locations.
Right.
I've got the sub point. I've got the latitudes and longitudes.
Sure.
And then I've got the closest city that I could find on Google Earth for that. So Cameroon. And this one here, I've put Lomé, Togo Middle, which is in the sea. So this was in the actual ocean. So I couldn't, but I put that these 2 cities, Lomé and Togo Middle, were closest to that point of the sea.
Sure.
And then I did the distances from each of those subsolar points to from Nottingham to those. I can then work out how fast the sun is traveling because it's traversed the distance across the land from Congo to Cameroon.
But why do you need why do you need I mean, if you know where the subsolar points are, can't you just find the distance between the subsolar points?
Yeah, but the distance between the areas, for instance, the distance from Durban to each of these subsolar points changes, and it's double the amount for the northern hemisphere. So if you see here, you've got 276 kilometers for one and 206 kilometers for another. And for mine, you've only got 81 kilometers, 67 kilometers.
So wait a minute.
The largest one.
So you're telling me that the subsolar point moved, and you just sorry, maybe I'm just being dumb. How did you calculate that 81 kilometers, which is the distance between the distance that the subsolar point moved in the go ahead.
Okay, so Blitz, just to confirm that we both have the same understanding of the subsolar point. The subsolar point, for instance, if you imagine forgetting UTC and all that stuff, let's say it's 12 o'clock or 1 o'clock midday or zenith, the sun will be directly above you, yeah? Now, 1 hour later, the sun is not going to be in that same location. It's going to be a different location. You agree with that, don't you, Blitz?
Yep.
Yeah. So because I didn't do all of these data sets, we tried to do these data sets 30 minutes apart, but so that's pretty close. 11:40 to 12:12.
Yeah. No.
So the subsolar point would have changed for each of these data points. So therefore, I had to.
So you have
I had to do it accurately and work.
Points.
Yeah. Yeah, that's right.
So then why not just find the distance between those subsolar points?
It's just because one of the things that I was trying to do was work out whether Google Maps is accurate or not. Because if we're seeing a difference of...
So where did the 81 kilometers come from?
Okay, so I think, if I'm right... sorry, it's been a long time since I did it, so I'm just trying to remember. Pardon me, I'm just trying to... Sun travelled 81 kilometers. I would have got it from somewhere for definite. I'm just trying to work out where we're from.
Trust me, I've been in a situation where you do a calculation and you don't remember how you got there. So that doesn't mean it's wrong. It just means that we don't know what it means yet.
Yeah. From what I recall, I took this number here and subtracted it from that. Simple as that. But it doesn't look like that number matches up right now. It could be that it does.
Could be right. That could be right. Almost.
Yeah.
Let me punch those numbers in really quick.
Okay, so
4, 5, 7, 1, 4,
punch
5,
the
7.
high.
Yeah, I'm getting like 80.5.
Yeah. So that's what I did, and because the distances then change, I had to do it a different way because you got the larger number on the bottom. For instance, if you take from here, it was 449, then it went 462, which was the opposite way
that's
around.
Weird, right? So those are the distances that Clint has. So this would say that the sun was getting closer and then further away. Oh no, that's
exactly.
possible.
This is what.
No. That's totally possible though. Imagine that like the sun is directly overhead to the northwest, and then as time goes on, it's directly overhead to the northeast. As it gets when it's directly overhead to the north, then it'll be closest, and then it'll get further away again. So that's not so surprising.
No, I agree with that, and that's the reason why I was doing those calculations. Because remember, we're doing two different models here. You're doing the globe model, and I'm doing the flat Earth model. And on a flat Earth, the sun is local, so these distances play a key part into telling us how far the different land masses are. So, for instance, from these two locations, I know that Clint is so far away from the sun, and I am so far away from the sun. And then from the different subsolar points, we can work out whether Google Maps is accurate or not, or whether we've got some kind of discrepancy. But if you look at a circle,
I don't know how this would.
Okay, so
yeah, go ahead.
Okay. So I'll make it a bit more simpler for you, so you can understand. Let's forget all maps and suns and stuff for a second. Let's just think of a plane circle with the North Pole in the middle. Yeah.
Mm-hmm.
From the North Pole, you draw a straight line to say the outer perimeter. Yeah.
Sure.
Now imagine that straight line moves across just a few degrees. What is the distance that is traveling? The larger distance will be on the outer circle, correct?
1 sec. I'm just going to draw this out. Then we both have something to reference.
Yeah. Oh, sorry.
So we have our North Pole, and we have a line, and then we have another line, and things like this. And maybe it's moving like this way, something like that, right?
Yeah. So if you just draw the two angles, the angles will be. So if you just draw an angle for each one,
I'll just have 2 points. Yeah. So let's just call that theta or phi.
Yeah. I mean, you can leave it just like that. Yeah. So if you take two dots, draw a dot in the middle, closer to there. Yeah. Just draw a dot there. Let's say that's me in Nottingham. Now draw one quite far away towards the bottom.
Maybe over there.
Yeah. Now, if you measure the gap between the smaller dot, the closer dot from left to right. No, not there. In between. So move across. Like go from that small dot, the first dot, to the other side, to the line. Yep, go across. No, just to the edge of the line.
Wait, which to here?
Just there. Now do the same with the other dot at the bottom, to the other side. Which is the bigger line?
Of course, this one is.
Yeah, and that's what we observe. That's what we observe with my data, which I'm showing you here now. Let me bring it back.
That's not what you were like. Those aren't the distances that you're measuring, right?
Those are the distances I'm measuring, because I'm showing here. Look, this is Clint's outer circle. Yeah, it's showing 270. Basically, it's double the distance. Virtually, I don't know what kind of relationship you want to call it, whether it's linear or whether it's logarithmic or whatever. But what I'm trying to say is the distance for me, it was exactly double the distance to get for that the sun traveled for Durban for Clint, and that's what I was trying to show.
So
which
and perhaps I'm wrong, but the way that I'm interpreting and I'm going to have to draw this in 3D because it's kind of hard to say. Hard to do away from 3D is. So here's our North Pole. And then say here's you. Let's call this
Yeah.
Riz. And then Clint would be
Yeah.
somewhere over here. Call it
Yeah.
Clint, right? And so maybe we have a line here, we have a line here, something like that. You guys are at different places. And so
Well, you could draw a line. You can draw a line in between as well for the subsolar point, and you can show how that moves.
yeah.
So
Maybe the
we
subsolar point is here.
Yeah, yeah. So if you draw like
Oh, that
four
makes
dots
sense.
across to represent the 4 different times, that's what
And
we're measuring,
maybe
the
like
distance.
here.
Yeah. Yeah.
So, and the subsolar point's moving like this way on your model or something like that.
Yeah.
So the thing that you're actually measuring is not these distances, but rather you're measuring something like how the sun moves from here to here, and these are the distances that you measured.
Yeah. In either case, from that, I'm able to deduce the speed being 250 miles an hour, which you would agree with, yeah?
Yeah, but I don't know why we would expect that that is further. I don't know why. So I mean, you picked an almost perfect day to do this. If you had done it on the equinox, it would have been perfect. But the sun should be basically right on the equator, so it should be basically the same distance from either of you, because you're both basically like one's in the north, halfway to the northern hemisphere, the other one's halfway down the southern hemisphere.
Yeah.
So like I don't know why this distance would grow faster or would grow slower than say this distance.
Yeah. Okay, so that is something I definitely observed in the experiments with the Americans and Brazilians and Arubian, Caribbean people. Basically, where the sun is rising, the shadow changes much faster because the angle's changing really quickly.
That's always the case.
So one of the things that you do realize is that in order to do this experiment accurately, you have to be above, the sun must have risen somewhat, because otherwise every second is you're talking a degree in angle change.
Doing it near noon is actually quite smart.
Yeah, that's what we try to do. But yeah. So Blitz, one of the things that you've shown now is exactly what I drew on my diagram. So, I don't know if you've seen my GeoGebra diagrams that I draw, but I drew one where I showed distance. Okay, well, just to give you an idea, I drew what you've just drawn on GeoGebra, and it shows the distance the sun is traveling, and that's what I showed people. So I don't know why people were crying that I showed that exact same model that you're drawing right now.
So I'm just trying to understand. So
if you just add one more subsolar point and do the same triangle, you'll see the same drawing that I drew. So
So we'd have one more subsolar point, like something over here.
Yeah,
and then we'd be interested.
Yeah,
So the distances that you're calculating, these the 81 kilometers and so on, that's the distance between this length and this length, right? Okay. That's the difference between those two distances. I don't know why that distance would be faster, like the rate at which that distance changes would be faster or slower between these two data points.
Yeah, so again, I agree with you, Blitz, that we have to investigate why certain things are happening. But one of the things that we have to agree on is our data is correct, that we both agree with the data
you produced is correct. My complaint is that I don't think that the speeds that you produced were meaningful.
Okay, so what speed would you calculate the sun being traveling from all the information I've provided you?
Basically, I would just calculate the distance of the... So one question I have to ask is, So the distance that I would calculate would be assuming that the sun stays at like the same height over time, over the course of a single day. Which presumably, I understand some flat Earth models require that the sun changes height over the course of a year, but certainly not over the course of a day. So I would just calculate the speed at which the subsolar point moves.
Yeah.
Yeah. So and that would just be the rate at which.
Could you do that and just verify what? Are you able to do that if it's not too difficult? Just so that everyone can see it. Okay. So locations or latitudes and stuff.
Latitudes, yeah.
Oh yeah, sorry. Okay then. So best if I turn the camera around
Starting
again
with
for
the
you.
one, so I have the latitude and longitude of the first subsolar point. What about the second one?
Yeah,
If you have that.
just 1 second.
Okay.
Yeah, I'm just getting it for you. I want to make sure you get it accurately. Let me turn off these props. Okay, hopefully you can see the screen. Okay, so are you wanting for Nottingham or for? Oh no, you're
Oh no
wanting
no,
just the
I just need
solar
the
point.
subsolar
Fine.
point. Yeah.
Okay, so the
So
second one, which was at 12:12, is 3 degrees 19, and then
3
37
degrees 19
seconds.
east, or no, 3 degrees 19 north.
Yeah,
Okay.
yeah. Sorry, not. And then east 10 degrees 53, and then 30.73.
Oh, 10 degrees. I'm just going to estimate that. What's 53 divided by 60? 0.88. Okay. Okay, so I'm getting a distance between those 2 points as, oops, it does not like how I entered that. I'm getting a distance of about 891 kilometers. And how long
Okay.
was between those two?
First point was 11:40. Second point was 12:12. So,
So that's 32
20,
minutes.
30. Yeah, 32 minutes.
So 32 minutes is how much of an hour? So it's 50.53 of an hour. So I'm getting a speed of 1,670 kilometers per hour.
1,007. Which in miles per hour?
Multiply.
Sorry,
by,
because
like,
I'm from the UK.
1.6, like 2,600 miles or so. 2,600,
2,600.
2,700. Yeah.
Let me just 1 minute. Let me just go on Google. 1 minute. Kilometers to miles per hour.
That actually seems wrong.
So, yeah, it should be less. It should be a lot less. Okay.
Actually, no, that's about right.
Okay, so how many kilometers per hour did you have it again? 1,000.
I had it at
Let's-
1,600. Yeah, no. I multiplied by 1.6 rather than dividing by 1.6.
Okay.
1,670 kilometers per hour divided by 1.6 is 1,043 miles per hour.
Okay, 1,000. Oh, I've got 1,057. Okay.
Yeah.
And
close.
you're doing that based on.
The distance between the subsolar points.
Yeah, but what I was doing is based on the distance between the two locations from the.
No, I
So,
know.
for instance, Clint's. Yeah, which is a real way of doing it because
the trouble. So it's a different. So the way that you measure it, you're measuring the speed at which a hypotenuse changes. But really, the thing that's actually changing is not the height. Sorry, my cam's black. The thing that's changing is not it's like it's this distance here, not the height of the hypotenuse. So you're getting a smaller number because basically, let me draw two triangles. So you're measuring the change between.
Actually, just 1 second. While you carry on, Blitz. I don't want to interrupt you while you're working on something. Go on.
So basically, what your calculation is doing is you have so I'll just draw a picture. Sorry, I can't draw a triangle like this. So here's Riz, here's the subsolar point, and here's the sun.
Yeah.
So so we have this hypotenuse h. It's called d. Call it d1, and then at a later point, the subsolar point is a little bit further away, and so you have a new triangle that looks like this, right? With a new subsolar point. And then you have some new hypotenuse, d2, right?
Yeah.
So what you're doing is you're doing d1 minus d2, or maybe.
Hello?
And you're getting like 80 something miles.
You broke
and
up.
the reason why you're getting
for a
that is
second.
because.
Yeah.
Yeah, so you're taking the difference between these two distances and dividing it by the time, right?
Yeah. Yeah.
But the thing is that's not actually the speed of the sun. That's not even the speed at which the sun is moving away from you. That is more precisely would be like, yeah, it's not even it's Yeah.
Remember, Blitz,
just
the
not
reason
not
why
a
I did
correct
it,
measure
that the
of
reason,
speed here.
yeah, no, I appreciate what you're
It's just
saying.
not a useful
But
measure, though,
what
right?
you've got to understand is, no, it's a very useful measure, and this is why I'm doing it. Remember, if I'd
But what
done
is
it,
it?
if
It
I'd
doesn't. It
just
doesn't
allowed
capture the
any
speed of
Glover to
anything.
do, okay, so Blitz, I want you
But
to
it doesn't
just
capture the
imagine
speed
for
of
a second
anything.
that it does capture the speed. It captures the speed of how the sun moves from point A to point B.
No, it doesn't, because it's moving in a different direction than your line of sight is. So you're not actually capturing the speed at which it's moving.
Okay, so
So
I'm not sure I
if
understand what you're
instead
saying.
of
I understand what
think
you're
of it this
saying.
way.
That what you're telling me is you can only measure this according to your model. You can only measure the speed of the sun from the subsolar
No,
point. Is
this
that
is
what you're
using your
telling me?
model. This is using your
No,
model.
no.
Yeah. I'm like
Yeah,
this is entirely flat.
yeah. Okay.
Right, I'm putting the sun as a local position. But the
Yeah.
trouble is that so if the sun went so let me give an example of when your calculation would be useful. If the sun went like this at the same angle, but it was in a new place, if it went from like here to here, and then you measured that, you have D1 is this distance, and then you have D2 is this distance, then your data would be correct because you're measuring distance along the same line of sight. But that's not the direction, in your model, that's not the direction the sun's moving. The sun's moving like horizontally, basically, right?
Yeah, I just want to make sure I understand what you're saying clearly, because I don't want you to maths me, not being rude or anything, but simply I want to
No,
make
I
sure that
understand.
you
You're good.
understand what I was trying to measure, because this is part of the reason why flat earthers won't discuss it with people, is because they don't take into account what we're trying to observe or do. And one of the key things here is that distance between the subsolar point, and I know you're showing it here, but why is that distance longer? No, actually, that's the wrong word. What I'm saying is, why did I calculate 250 miles an hour for both of them while you're calculating 1,000 miles an hour? That's what I'm trying to work out.
Right. So we could. So the reason why you got 250 miles an hour is because, I mean, in this picture, right? These distances D1 and D2 are going to be very close to each other, right?
Yeah.
Just because this distance, like that distance, that difference in distance is small, and compared to the height. But in my model, and so in fact, like this difference in distance will be smaller than the difference here, much smaller. In fact, we could actually compare that.
Yeah.
Like that,
Okay.
and so
Okay. So just
right.
one second.
So you
While you're doing that, I'll pull up my calculator and just do my distances again. And you carry on doing what you're doing, and then I'll just
can you
double
actually
check.
give me your distances between the two? Can you give me the
So
distances between your two, like the first 2 points for you?
yeah, just once. Yeah, so 81 kilometers and 133 kilometers for the subsolar points, and then
Actually, can you give me can you give me the second distance? So I have your first hypotenuse. Can you give me your second hypotenuse?
second one was 44908, so 4,490 kilometers.
Wait a minute. Hold on. That's not the hypotenuse. That's the distance above the different distance above the subsolar point.
Okay, sorry. Hypotenuse. Let me just see. Did I write it down?
Wait a minute. Were the values that
Not
you
in
were
the.
subtracting the hypotenuse or the subsolar points?
There was a subsolar points.
So we were subtracting heights above the subsolar points. So really, we were
Yeah.
measuring vertical displacement. We were measuring the sun moving up and down, not side to side. That's
Sorry,
what
no.
your calculations measured.
Okay, so 1 minute. It's just because it's been so long since I did this, I can't remember. But from what I remember,
No, you're good.
I did the distance to the sun, meaning the base, not the hypotenuse. But for some reason
Yeah, yeah,
today, your numbers
right.
are
So
your
so you
numbers
have
are.
so
Yeah.
I misinterpreted what you were
So
doing. That's my bad. So, but
yeah.
the data that you have is more akin to this for
Okay.
the speed.
Okay.
So you're seeing a difference in. No, let me draw this differently, and then something like this.
So just 1 minute. I'm just typing in these numbers again.
So
67,
you were comparing
281.
these heights.
Yeah. Okay. So just 1 second. I'm just working out exactly how long. So I did the experiment over 1 hour and 6 minutes. So just 1 second.
Sure.
So no, I'm just trying to see. It's just sometimes I don't write all the details on the actual thing that I was doing. I was just writing the
You're
numbers.
good.
So I could be missing a number. So I'll just put this into
By the
memory.
way, I do
281.
have to go to bed sometime soon because I have a meeting tomorrow
Okay,
morning
yeah.
at 9 at the bank.
Oh yeah, the Blitz. We can
It's going to
redo
be
this
very
tomorrow,
fun.
and we could, or whenever you're free. I don't want to hold you up. I've got the other data that we can go through as well. But what I want to clarify is that let's say the number of 250 miles an hour, which I got, is accurate. I want to know why we're having a difference of opinion here
But
because we
what
shouldn't.
is that a
Because
measure of? I
I was simply
is that a
using
but
the
I just
distance. So, okay, so the measure, it was between the different points of time that we did, the distance that either the sun traveled or the distance that it traveled from location to location. But that was, the same for whether it's from Nottingham to the subsolar point or from Durban to the subsolar point. It was 250 miles an hour.
so when we did that 40, so if I remember correctly, can you pull up your data again really quick?
Yeah,
Just
no
so I
worries.
can,
Just one
because I
second.
just want to settle this before I go to bed.
Yeah, no, definite, because I just don't understand that we're having.
Yeah, no.
Because a
I
few
think I
times
can
Blitz today
explain
that
it.
yeah. So, um, I
Okay,
mean,
so
this is
the
what I would have used to
4,000.
calculate the
Yeah.
speed. Yeah. So those
Right.
numbers
So that
there. The top one is
4,571,
Nottingham.
4,409. Yeah. Okay, so 4,571, 4,490. Those are the difference. You took the difference of that and you got 81 kilometers. Those are the heights,
Yeah.
right? Those are the, those are the heights at between different, the heights that you would calculate you used trig, I
Okay.
used ratios. It's the heights that you get here. It's this
Okay.
h
Yeah.
for the two
H.
different
Yes.
times.
It's
So
definitely H. Yeah.
really,
Yeah. That's right.
yeah. So your measure, so
So
that
you're saying I was
250
measuring
kilometers
vertical
or miles per hour
distance?
that you get, yeah, you were
Was
measuring
vertical
vertical
speed?
distance. That's the
Okay.
you're measuring a speed of the change in the vertical distance over time.
Okay.
That's what that
Okay.
250 kilometers is. Whereas I was measuring
Okay.
horizontal distance,
Okay. No, I agree with you then.
which we agree
So,
is just the distance of
yeah.
subsolar point.
Okay. So you got 1,000 miles an hour for horizontal, and I got 250 miles an hour for the vertical distance. Yep. That
But
sun is traveling.
importantly, in
Yeah.
your model, it should not be moving
Yeah.
vertically, right? Like that's an important
Not
thing. Like if it's moving vertically, that means that the sun has to be jiggling up and down in the sky during the day.
okay. So Blitz, just to clarify that. Remember, we're still trying to work out our model correctly, but you would agree that if there was a so-called firmament which had a lensing effect of some form, that it would appear that the sun would change heights when it's going over, say, a different part, which is possibly, or are you saying no? Because
Maybe.
I've observed the same. Yeah.
I mean, I don't know. Like it depends on
Okay.
what the
So
firmament's made out of. We could do that calculation if
okay.
we wanted to, but
So no.
can we say this sufficient? Can we say this certainly that? Well, wait a minute. That a sun that just moves at a fixed level height above a flat Earth is not consistent with the data that we've looked at.
Say that
Disregarding lensing
again, just to me.
effects, so if we disregard lensing effects from a possible firmament, and we say that the sun over the course of a single day doesn't move up and down, that a flat Earth model is inconsistent with that data. Maybe if we introduce lensing effects, maybe if we allow the sun to move up and down, then it could be consistent with the data. But currently, stationary horizontal sun, no lensing effects is not consistent with the data we have.
Okay, so Blitz, what I'm trying to say is that one of the key things we was trying to look at here is prove a local sun or faraway sun. We haven't done that.
Yep.
I've done my part, which is prove a local sun, but you haven't shown me 93 million miles today.
How have you proven a local sun?
You've got all those heights there, which show that it's within 1,000 kilometers or 1,000.
Well, wait a minute. So the point is if you assume a local sun, then those heights are the calculated height of the sun. But if those heights disagree with each other, that means that your assumption is wrong, because they can't have different heights at the same time. So rather, the claim is that. So the reason why you need 2 points, not just one, is because.
Yeah.
Go ahead. So the reason you need 2 heights and not just one is because one of the the reason you need 2 measurements and not just one is because one of the measurements will fix the height and the other one will check the height. And so let's say that we would use your measurement in Nottingham. We would say that, okay, according to your measurement in Nottingham, you should get that the height of the sun above the Earth at that moment in time is just under 4,600 kilometers.
Okay.
And then we say, okay, if the sun is just under 4,600 kilometers above the Earth at that moment in time, how long should the shadow be in Durban in South Africa? And then we see, well, wait a minute, that's not consistent with what we observe. In order to be consistent with what we observe, you'd have to see a height of 5,500 kilometers, not 4,600 kilometers. So this is saying that actually a flat Earth local sun is inconsistent with the data with an error of about 10 or 11%.
Yeah. So
now,
I can agree with what you're saying in terms of
Go ahead.
Yeah, but what I'm trying to say is,
the alternative
remember, Blitz, just 1 second. I've been trying to say this for a little while, is that you're still, you're neglecting quite a lot of the flat Earth perspective out of there, which is the firmament, and that one of the statements that you made is that you can't have 2 different heights. Well, what I'm contending is that there's a possibility that could happen, and that could be observed due to lensing.
If we add more assumptions to the hypothesis.
Yeah.
If we add more assumptions to the hypothesis, for example, lensing, or perhaps that, it would just have to be lensing, then perhaps that is consistent with the data. But a flat Earth with a local sun and no lensing is not consistent with the data. It's just straight up, it's your data, it's not consistent with the data. Now, we can look at the round Earth model and see if the round Earth is consistent with the data.
Yeah.
And we find that it is to within 2% error.
Okay, so what I'm trying to say is I've got lots of data. I've got 3 different data sets for you on here. You should be able to provide me the 93 million miles within 1% or 5%.
All I need to do is provide you a consistent radius of the Earth. This calculate, and I've mentioned this in other lives. Maybe you've been there, maybe you weren't. But the round Earth calculation does not posit to calculate the exact distance the sun is away, just that it's distant.
Okay.
Just that it's more than say 10 or 100 times further away than the radius of the Earth.
Okay.
But instead, my result has to come up with a consistent radius calculation of the Earth.
Okay. So this is where
the competition.
So just to, I understand that, but just to remember, Blitz, I'm trying to be a representative for the community I'm trying to represent here. Yeah.
No, I know.
Which is they would say you're basically, and I fully respect you, and I've got no qualms about what you're saying. I respect what you're saying right now, but what they would say is that you are using maths as a language to kind of neglect the point we're trying to make here, which is with using that data, which me and you both have, I can work out that the sun is local, but you're saying for your model, you can't work out exactly where it is, which is going to be a major point for the flat earthers. Yeah.
No, but
for you,
you can't. Because in order for you, in order for you to have a local sun, according to your model, you would compute that the sun is at 2 different heights at the exact same time, which says that model, the starting assumption, is inconsistent. my model doesn't purport to compute the exact distance from the sun. Instead, it purports to calculate the radius of the Earth. So the game is this. If your model is correct, you will compute consistent heights of the sun across different locations. If my model is correct, I will compute consistent radii of the Earth across different locations. So those are the things that we have to compare. Does your data predict consistent heights? Does my data predict, does the data predict consistent heights of a local sun or consistent radii of a distant, for a curved Earth and a distant sun?
Yeah, I understand what you're saying, Blitz. Just 1 second. Let me just get this prop off again, just to show you something.
Sure.
Because this is very important, Blitz. I don't want it to be ignored. Yep.
No.
So here's the bottle. Yep. Very simple. Let's just pretend for a second that this bottle represents the dome, firmament, or whatever. You would agree, and please confirm you agree, that this point here on the side of the bottle is lower than this point here on the top of the bottle. Yeah.
Sure.
Yeah. Now let's imagine the sun is right here. Yeah. In between them 2 points. Yeah.
Go ahead.
Yeah. Sorry. If you need to say that, that's not a problem. I don't mind coming back on if it's important.
No, it's not a phone call. It's an alarm.
So yeah. So what I'm trying to say is, if we take, for instance, the x-axis here, which is going across horizontal here, and then the z-axis vertical, and we take the sun to be in between those positions. Now let's imagine for a second Clint's down here across, remember a flat Earth model, but I'm over here on the right here. Would the sun appear to be at two different heights due to this scenario here?
No, the point is we calculated the sun's, we calculated the sun's height above the Earth.
Yes, but
right. So that's
the Earth is inside. The Earth is inside here, for instance, in this example, where I might add the water is level and flat, as you can see there. Yeah. So the Earth is inside there.
Yep.
This is the firmament. We're representing the sun is outside the firmament here.
Yep.
Yeah. So that's what I'm trying to do. So what I'm asking you from a mathematical physicist. Yes, but we're at two different locations.
Distance, and that's going to be measured the same in either case. Yeah, that's going to be the same in either case. So remember when you did the experiment with the Nerf darts?
Yeah. Yeah, I remember.
The conclusion that we came to is that if you have a local sun flat Earth, then if you double the distance, the shadow length should double. That was the conclusion we came to, right? So basically, the ratio of the distance to the shadow length should be consistent between all data points. That's the game here. That would prove your model. But we can check that with the data that you have. The distance, I can punch it in right now. The ratio your shadow length was 1.27 meters, and the distance was 5,831 kilometers. That's a ratio of 0.000217. Right. Then we can do the same thing for Clint. So his shadow length was 0.705, and his distance was 3,864.28 kilometers. That's a ratio of 0.000182. Those ratios are different. And in order for your model to be correct, they have to be the same. That was the conclusion we came to in the Nerf dart example. Now, if you want to say that, well, maybe it's more complicated, maybe there's some lensing effects, sure, but that's not the same model as the Nerf dart thing that we were trying to test.
No, remember the Nerf dart thing, we've got two different locations here. We haven't got, remember when we was doing the Nerf dart, we had equidistant distances between the darts. Here we don't have equidistant.
The Nerf dart was over 1 point. No. The Nerf dart was over the far point, and then you had the two distant Nerf darts.
Yeah, which were equal distances apart.
So it's the same thing. Yeah, but that doesn't matter. Okay, it's just the ratio that matters.
Okay, so I know you want to go, but it's important. I mean, we can schedule to redo this later on when you're free, because I don't want to keep you up, but I want to actually check the ratios, because this is quite important. The ratios for all four locations, for all four times, and for both locations, Nottingham and Durban. But I'm happy to wait till tomorrow if that's what you want to do, so you can get some sleep, because it's important for you as well.
Yeah, probably should.
Okay, then.
Probably.
So we'll leave it till tomorrow. So just to, yes. That's fine. To recap, tomorrow we will do the ratios for the shadow lengths. If you're free, not a problem.
Okay.
If you're not,
Yeah. That's fine. Message me, and if I'm around, I'll message you back. It might have to wait till Wednesday or Thursday.
no,
Because,
that's not a problem.
things go on.
I'll
But
recheck. I'll check.
Message me, and we can figure it out.
Yeah, okay, no worries. I'll check all the data I've got as well, and it'll give me a chance to familiarize myself with the stuff again. Yeah. All right.
All right.
Anyway, thank you, Blitz. I appreciate your help. Yeah.
Talking with me. Take care.
No, you're welcome. Take care now.
Bye-bye.
Bye. Bye.